In this video, we're going to look at using differential equations to model motion where air resistance is an important term to be considered within the motion. Unfortunately, there are no nice rules for calculating air resistance or the drag acting on a body. Much will depend on the shape of the body and of course its speed. In practice, engineers will use wind tunnels to get some idea of the rules governing the air resistance or the drag acting on, for instance, a car, a motorbike, or indeed an aeroplane. For the simple mathematical models that we'll be considering, the air resistance is assumed to have magnitude which is either proportional to the speed of the object or to the square of the speed of the object. Air resistance will obviously oppose the motion of the object, so it will act in the opposite direction to the velocity. So let's start with an example. We've got a stone of mass 0.4 kilograms, falls from rest and experiences an air resistance of magnitude 0.112 V newtons, where V is the velocity. We've got to find the maximum possible speed of the particle, an expression for the speed V at time t, and an expression for the distance fallen x at time t. And we want to draw velocity time and displacement time graphs for the motion. So, as is usually the case with mechanics problems, we need to start with a diagram. So there we are, at t equals 0, it's at its initial height, and then at some later stage it is fallen a distance x and is moving downwards with velocity v, and the acceleration downwards. Now for the first part, well, for the acceleration, we'll write it as being dv by dt to begin with at any rate. Forces acting on the particle are its weight and the air resistance of 0.112 V. So if we apply Newton's second law downwards on the particle, we're going to get 0.4 G minus 0.112 V equals the mass 0.4 times A. In other words, we've got 3.92 minus 0.112 V equals 0.4 dV by dt, or dividing through by 0.4, we've got 9.8 minus 0.28 V equals dV by dt. And this is going to be a basic equation that we're going to use both for part A and for part B. Now, if the stone was moving at its maximum possible speed, then there's not going to be any acceleration acting on the particle. So we've got dV by dt equals 0. So that tells me that 9.8 minus 0.28 V must equal 0. So we've got the maximum speed is 35 meters per second. Moving on to part B, and returning to the differential equation that we'd set up in part A, we've got 9.8 minus 0.28 V equals dV by dt. Now this is one of these equations that can be solved either by separating the variables or by using an integrating factor. We'll do it by separating the variables again. So separating the variables, we've got, if we divide each side by 9.8 minus 0.28 V, we've got 1 equals 1 over 9.8 minus 0.28 V times by dV by dt. Integrating each side with respect to t gives me the integral of 1 with respect to t is equal to the integral of 1 over 9.8 minus 0.28 V times by dV by dt, and that's got to be integrated with respect to t. But we know that that can be also thought of as being the integral of 1 over 9.8 minus 0.28 V integrated with respect to V. Doing the integration then, we've got the integral of 1 is just t plus c. The integral of 1 over 9.8 minus 0.28v integrated with respect to v is going to be 1 over minus 0.28 times by the logarithm of 9.8 minus 0.28v. Now when t equals 0, we've got v equals 0. So that gives me that c must equal 1 over minus 0.28 times by the logarithm of 9.8. So I've got t minus 1 over 0.28 logarithm of 9.8 equals minus 1 over 0.28 times the logarithm of 9.8 minus 0.28v. If we multiply up by 0.28, we've got 0.28t minus the logarithm of 9.8 equals the logarithm of 9.8 minus 0.28v. So 0.28t is going to equal the logarithm of 9.8 minus the logarithm of 9.8 minus 0.28v. In other words, we know that if we're subtracting two logarithms, we're basically finding the logarithm of the division of the two quantities. So we've got 0.28t equals the logarithm of 9.8 over 9.8 minus 0.28v. But we really need to make v the subject of this formula, because we are asked for an expression for the speed of v at time t. So, first thing we can do is raise each side to the power e to get rid of the logarithm. So we've got e to the 0.28t is 9.8 divided by 9.8 minus 0.28v. Rearranging, we've got 9.8 minus 0.28v equals 9.8 divided by e to the 0.28t, or in other words, 9.8 minus 0.28v equals 9.8 e to the minus 0.28t. Rearranging this equation gives me 0.28v equals 9.8 minus 9.8 e to the minus 0.28t, which is the same thing as 9.8 times by 1 minus 0.28t, and then dividing through by 0.28, I obtain v is 35 times by 1 minus e to the minus 0.28t. Now if we use a graph drawing package just to sketch the graph of this, we can see that we're getting a graph where v simply increases from 0 and approaches a limit of 35 meters per second. And if you remember, 35 meters per second was the maximum velocity, or sometimes called the terminal velocity, of the stone as it was falling. So we've got v is 35 times by 1 minus e to the minus 0.28t, but of course v is simply dx by dt, where x is the displacement. And I can now obtain an expression for x by simply integrating this expression. So we've got dx by dt is 35 minus 35e to the minus 0.28t. So integrating will give me x equals 35t minus 35 times 1 over minus 0.28 e to the minus 0.28t, add c, which becomes x equals 35 plus 125 e to the minus 0.28t plus c. Now we know that when t equals 0, x is 0. So we've got 0 equals 0 plus 125 plus c. So c must be minus 125. So we've got x is 35t minus 125 plus 125 e to the minus 0.28t. Now, the displacement x at any time is certainly going to be bigger than 35t minus 125, but it's also going to be less than or equal to 35t. And as t tends to infinity, we know that x tends to 35t minus 125. So on the graph, what I've got, the solid line is the graph of x against t, whereas the dotted lines are the line x equals 35t and x equals 35t minus 125. Now let's move on to a second example. We have a toy rocket of mass 4 kilograms is fired vertically upwards from ground level with speed 20 meters per second. When the speed of the particle is v meters per second, it experiences air resistance of magnitude 0.8 v squared newtons. We've got to find the maximum height obtained by the particle, the speed with which the particle hits the ground, and the work done against air resistance during the motion. And we need to state any assumptions that have been made in answering this question. Again, we need to start with a diagram. So we'll begin by just considering the upward motion of the rocket. So the start there, we've got an initial velocity of 20 meters per second. At time t, we've got the rocket at a height of x meters above the ground and moving with speed v. And then we've got to put the acceleration on. Acceleration needs to be in the same direction as the velocity, so that's going to be upwards. We're looking for relationships linking the velocity to the distance moved, so we want to put the acceleration as v dv by dx. Forces acting on the rocket at this stage, well, we've got the weight downwards and we've got the air resistance opposing the motion, so that's also going to be downwards. And when the rocket reaches its maximum height, we'll suppose that maximum height is h meters, and we know at the maximum height the velocity of the rocket is going to be 0. Applying Newton's second law upwards for this upward motion of the rocket, we've got minus 4g minus 0.8 v squared equals 4a. Dividing through by 4 is going to give me minus 0.8 minus 0.2 v squared equals v dv by dx. That's just the acceleration term. And we can solve this equation by separating the variables. So writing the left-hand side as just being minus 0.2 times 49 plus v squared first of all. So we've got minus 0.2 times 49 plus v squared equals v dv by dx. And attached to this differential equation, we've got initial conditions that when t equals 0, we've got x equals 0 and v equals 20. So there's my differential equation. Dividing through by 49 plus v squared gives me minus 0.2 equals v over 49 plus v squared dv by dx. Integrating each side with respect to x gives me the integral of minus 0.2 with respect to x is equal to the integral of v over 49 plus v squared times by dv by dx with respect to x, which simplifies or can be rewritten as being the integral of v over 49 plus v squared with respect to v. So carrying out the two integrations, we get minus 0.2x plus c equals 1/2 of the logarithm of 49 plus v squared. Making use of the initial conditions, when x equals 0, we know that v equals 0, in which case that tells me that c must be a half of ln, or half of the logarithm of 49 plus 20 squared, in other words, a half the logarithm of 449. So we've got minus 0.2x plus 1/2 the logarithm of 449 equals 1/2 the logarithm of 49 plus v squared. Rearranging that gives me 1/2 of the logarithm of 449 minus the logarithm of 49 plus v squared must equal 0.2x. In other words, x must be 5 over 2 times by the logarithm of 449 divided by 49 plus v squared. Now, when it reaches the top of its motion, we've got x equals h and v equals 0. And substituting that in, that gives me h equals 5 over 2 times by the logarithm of 449 divided by 49, which is approximately 5.54 meters. So we now know that the rocket goes up 5.54 meters. So we now need to move on to considering the downward motion of the rocket. So it starts at its maximum height, and then after time capital T, it has fallen distance y from its maximum height and is now moving downwards with velocity v. And the acceleration, again, because we're looking at the relationship between speed and displacement, we want to write the acceleration now as being v dv by dy, rather than doing a dv by dt type expression. Forces we've got acting on the rocket at this stage are its weight and the air resistance, which is opposing the motion. And then when the rocket is about to hit the ground, we're going to suppose that it is moving with speed or velocity capital V downwards. So Newton's second law applied downwards is going to give me 4g minus 0.8 v squared is 4 times a. Dividing through by 4 gives me 9.8 minus 0.2 v squared is v dv by dy. That's the acceleration term. Or 0.2 times 49 minus v squared equals v dv by dy. And this differential equation, we have got initial conditions that when t, capital T is 0, so at the start of the downward motion, y is 0 and v is 0. So we've got this differential equation to solve, which again we can do by separating the variables. So we've got 0.2 equals v over 49 minus v squared times by dv by dy. Integrating each side now with respect to y gives us this. And, as usual, we can cancel out, if you like, the dy's. So we've got the integral of 0.2 with respect to y is equal to the integral of v over 49 minus v squared with respect to v. So we've got 0.2y plus c is minus a half of the logarithm of 49 minus v squared. When y equals 0, we know that v is 0, so that tells me that c must be minus a half ln logarithm of 49. So I've got 0.2y minus a half logarithm of 49 equals minus a half the logarithm of 49 minus v squared. In other words, we've got 0.2y is a half of the logarithm of 49 minus the logarithm of 49 minus v squared, which gives me that y must be 5 over 2 times by the logarithm of 49 over 49 minus v squared. Now what we're trying to do is we're trying to find out the speed as the rocket hits the ground. So that's when the value of y is equal to the maximum height obtained by the rocket, which was 5 over 2 times the logarithm of 449 divided by 49. So I've got the equation 5 over 2 times the logarithm of 449 over 49 is 5 over 2 times by the logarithm of 49 over 49 minus capital V squared, where capital V is the speed that the rocket hits the ground at. So cancelling out the 5 over 2's and then raising each side to the power e, we end up with 449 over 49 must be the same thing as 49 over 49 minus v squared. In other words, 49 minus v squared must be the same thing as 49 squared divided by 449, which gives me that v squared is 49 take away 49 squared over 449. And that gives me a final velocity of the square root of 19600 divided by 449, or if you like, a final velocity of 6.607 meters per second. So the rocket hits the ground with a speed of 6.607 meters per second. Now for the final part, we were asked to work out what was the total work done against the air resistance in the rocket's motion. And the work done by the air resistance is going to be precisely the loss in kinetic energy during the full motion of the rocket. Because the rocket started at ground level and finished at ground level, so there's no change in the potential energy. So the loss in kinetic energy was its initial kinetic energy, which was a half times 4 times 20 squared, minus the final kinetic energy, which was a half times 4 times 6.607 squared, which ends up being 702.7 joules of energy has been lost. Okay, and that energy that has been lost is precisely the work done against the resistance. The assumptions that we've made in answering this question, well, we've certainly treated the rocket as a particle, and we've certainly assumed that there's no wind producing any sideways motion, so that the motion of the rocket is purely vertical. And there's been no collisions with any birds or anything else flying around during the course of the rocket's motion. So that ends our look at the use of differential equations to model air resistance.